what an absolute beast The Rock Dwayne Johnson was, right, when he was doing this battle ropes, right? This video was extracted from his Instagram a couple of years ago, right? So why is it that I'm showing you this video? Not that because I'm a huge fan of his, but this battle ropes has everything got to do with the topic that we are going to learn today, which is waves. What an absolute beast Dwayne The Rock Johnson was doing, right? He was doing the battle ropes, right, on a set of very heavy ropes. Some of you might have seen this exercise before, some of you might have done it before, right? But why am I showing you this video, right? Because it has everything got to do with the topic that we're gonna learn for today, which is waves. Okay, so when we talk about waves, right, typically we think of the waves that you see in water, in oceans, you know, or in any water body such as the one shown in the screen, right? Okay, but of course waves can be generated on not just water, can be generated on a lot of different objects, okay, as you will see in this chapter today. But first, just now what you observed was a battle rope, right? And you can see that the exercise, you know, involves creating a wave-like pattern. You can see here, right, in a set of very heavy ropes. Okay, this exercise is very strenuous. It involves endurance, strength, and cardio. Definitely, what a great exercise, right? But there are many different types of waves that we can think about. If we look at this example here, you have the typical water waves. You have, what is this? This is a sound wave, right? This is a speaker and the sound waves generated from a speaker. You can see another wave created in a ribbon in the Olympics. And if you look at this, I hope you all recognize this. This is a glass prism, a triangular prism, right, that you know, spits up white light into the different colors, the rainbow colors, right? So light is also a type of wave. And of course, our all familiar, right, what is this? Infrared radiation, right? We learned in chapter 7 that this is thermal radiation, one of the ways that one of the modes rather that thermal energy can be transferred, right? Thermal radiation in the form of infrared is also a wave. So you may have heard people say that, you know, infrared wave, right? It's also a wave that we cannot detect with our eyes. But on the other hand, you know, the visible light, right, our rainbow colors can be detected by our eyes. The sound waves can be detected by our ears. And of course, not forgetting our all Singapore favorite Kallang wave. That's right. Kallang wave is also a type of wave as the name suggests, but just this is created among the crowd of, you know, audiences, right? Alright, without further ado, let's get right into the topic. Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we're going to learn about waves. Alright, this topic is rather big. There are a lot of terms to remember, but the number of formulas is quite little, about 3 formulas around there. Alright, so I hope we can absorb whatever that we need to learn for this topic. Okay, let's get right to it. Okay, so first part, we're talking about wave motion. Alright, so we need to recall what is the definition of a wave. Okay, what is the meaning of a wave motion using, you know, vibration in ropes, right? Remember that we're looking at the battle ropes. We can create a wave in ropes, right? And then understanding that waves transfer only energy, but not matter, right? So wave only transforms energy, but it does not transfer matter. Alright, we'll take a look more about that later. So first of all, what is a wave? What's the meaning of a wave? Here comes the definition. Remember, for all definitions, please commit to memory. What is a wave? What's a wave? A wave is a disturbance. Alright, disturbance. Right. When you think about this word disturbance, let's think about water, right? If you have an absolutely still, you know, water surface, think about a lake, a very calm lake. Right, the surface of the water is very still, there's no movement there, right? In order to create a wave, what do? You have to create a form of disturbance, isn't it? By, for example, throwing a pebble into, you know, into a lake, right, onto a water surface that generates a wave, a ripple, or a wave. So it has, it has to do with a disturbance, right? You need to have a disturbance in order to create a wave, right? So wave is a disturbance that transfers energy and only energy from one place to another, right? So this is the definition of wave. So what does it mean by disturbance? As I was saying just now, right? In order to create waves in a tank of water, for example, all right, you need to have an object, right, that creates a disturbance. So over here what we have is like a dipper. This thing is called a dipper. It constantly moves up and down, up and down, up and down, and it creates a water wave in this tank of water, right? So in this case, the disturbance is caused by some object vibrating up and down in the water. It could be due to anything that disturbs the water, right, that causes a disturbance. Okay, moving forward, okay, this is something that that can be quite confusing to some people, but do pay attention, right? So just now I was emphasizing a lot that waves only transfer energy but does not transport matter, right? So what do I mean by that? Okay, so if you look at the water tank just now, it's clear that this dipper, or this vibrating object, this guy called the dipper, it has kinetic energy, isn't it? Because it's constantly moving up and down, right? By moving up and down in the water, you see that this dipper actually causes a wave, you know, and what happens actually is it has transferred its kinetic energy to the water, causing a wave. And you can see that the energy, the kinetic energy that's transferred to the waves, you know, is being being transported in this direction, which is actually the direction of where the wave is going, you see, to the right hand side. Okay, so actually this vibrating object has passed on the kinetic energy onto the water, creating this motion. You see, the water now starts to move in terms of a wave, in the form of a wave rather, right? So you can see that, you know, kinetic energy has been transferred, right? So this part is clear. But a wave does not transport matter. Okay, what do I mean by that? Okay, let's look at this rubber ducky, right? This rubber ducky, some of you might have played with it in the bathtub when you were young. Okay, so if you put a rubber ducky on, you know, on the water, on the surface of the water, and you create a wave, for example using your hands, okay, what you will see is that the rubber ducky will move up. In this case, you know, if you look at the height of where the rubber ducky is, it has moved down from here to here. It's moved down, and then you continue to move down, and then you then later move up, you know, along with the wave, okay, according to the wave. But what you realize is that the rubber ducky will not, I repeat again, will not move in this direction. Okay, even though the wave is going to the right hand side, but if you do it carefully, you will realize that the rubber ducky actually does not move to the right. Okay, now to prove that, I have another video to show you. Okay, let's take a look.
A dipper into the tank at one end produces a series of simple waves. The waves move along, but place a float in the water and it stays where it is.
Alright, so from that video you can actually see that the floating object really does not, you know, move in the direction of where the wave is traveling. Or rather, it only bobs up and down. So this proves that, okay, wave does not transport matter, right? This object floating in the wave, you know, on the wave rather, does not travel in the direction of the wave. Okay, so it does not transport matter. So recap again, right? A wave transfers or transports energy from one point to another in the direction of the wave transfer, but not any matter that is floating or floating on the wave itself. Okay. Okay, so here's what a wave looks like. Okay, okay, a wave in water. Here we are looking at a water wave. So the wave is made up of water molecules, of course. Okay, now in this case, the wave is traveling to the right hand side from left to right. Okay, so let's examine every water molecule along the wave. Okay, so you can see here this water molecule on the wave itself, right? So let's zoom in a little. Okay, this blue color line represents the wave before, and the dotted one is the one that that represents after. That means after, for example, half a second, right? You know that the wave has traveled to the right hand side. So this one is the before, and while this one is the after. Okay, so after a very short time, the wave has moved to the right hand side. Alright, so while the wave has moved, let's look at how the water molecules along the wave has moved. Okay, so let's zoom into one guy. Okay, let's say here, this guy here, right? before the wave has moved to the right a little bit, it was here along this blue color line wave. But as the wave has traveled to the right hand side, look at the after. Now this particular water molecule is now here. Okay, so essentially it has actually moved downwards. Okay, it did not move to the right hand side. No, this is wrong. Okay, why? Recall that a wave does not transport matter. That means any water molecule, right, on the water wave will only move up and down, just like the rubber ducky. Okay, I hope this is clear, right? Not just any object placed on the wave, but the water molecules that make up the water wave, right, will only move up and down. So before it travels, the particle is here. After the wave has traveled a little bit, now that the particle is here, so we know that it has moved down. So if you can look along the wave, you can see, right, some particles actually move up, some particles actually move down, but none of the particles move right or left. Okay, so let's look at a common question. This is a very, very common question. Okay, you have a wave. Okay, need not be water, right? It can be anything. It can be a rope. Okay, so I have two molecules P and Q that are along the wave. Okay, let's think of this as a string. Okay, so you have the string molecules making up the string, right? So you have molecule P along the string, and string molecule Q. Okay, and the wave is moving to the right hand side. Question: in which directions are these two molecules moving at this instant? That means you know that the wave will travel to the right, and you know the molecules will vibrate, okay, along the wave. But in which direction are they going to travel at this particular instant? Okay, so to answer this question, it has to do with this. Okay, you can see there's a before, there's a after, right? So let's treat this as the before, okay, and we will draw the after. Okay, so the wave is traveling to the right after some time. Okay, I'm going to crudely draw it. Okay, something along this line, right? You can see that now the wave has traveled to the right hand side. Okay, it's displaced a little bit to the right hand side, and now given that the red color line is the new wave, where is P gonna be now? So now P is gonna be here, just above it, and you can see that P has moved upwards. Okay, on the other hand, looking at this the red color, looking at molecule Q, right? Q, particle Q, it has now been pushed outwards, moved upwards, right, to this particular spot here. So Q also has moved upwards. So that means in the next instance, both P and Q are gonna be at a higher position compared to this current position. Alright, means that at this instant, P and Q are both moving upwards. Okay, so P upwards and Q also upwards. Right, so that's the answer for this question. Alright, but we can examine another particle that is moving downwards at this instant, right? So let's say here. Okay, let's find another particle here. Let's call it R, PQR, right? Where is R in the next instant? Well, if you are sharp enough, you know that it's here, right? R will be here. So essentially, at the next moment, R will be at a position lower than it is now. So R at this point in time, you know, at the black color wave, where the black color wave is, at that moment it will be moving downwards. Alright, I hope this is clear enough. Okay, if not, we will look at a simulation later. Okay, so oscillation. Alright, so part 3, this word oscillation, oscillatory motion, or rather this word oscillation, you would have seen this. Okay, you would have seen this motion, this name, when you look at pendulum. Alright, the swinging of pendulum from left to right is what we call a oscillatory motion. Now, this part 2 says that is the oscillatory motion of particle in a wave. Why do I say that a particle on a wave moves in the same way as a swinging pendulum. Okay, for that we have to take a look at another slide. Okay, as you can see here, okay, I've animated the, the pendulum and the particle in the notes, okay, using the PowerPoint slides here. Right, you can see that the pendulum, right, on the right hand side swings from A to B, back to A, back to B, right? Likewise, you can see that that particle along the wave, right, is also moving between points A and B, right, between two extreme points A and B. So you can see that they both behave, move in a very similar way, and this similar way is what we call the oscillatory motion between points A and B, right? Just like this pendulum here. All right, so again, a particle in a wave, move in the same way as a pendulum, right? As a pendulum bob. Okay, so you can go check out this wave motion simulation on this QR code. Is in your notes. Okay, right. So oscillatory again comes from the word oscillation. Okay, refer back to pendulum motion when we study about pendulum. Okay, so let's summarize a little bit. Okay, a wave comes from a disturbance, right, which is the source of the wave. Right, wave transport energy but does not transport matter, and along the wave, all the particles along a wave move in oscillatory motions. That means they move to and fro to extreme points like a swinging pendulum. Okay, let's look at part 2, which is the type of waves. Okay, so just now what you have seen so far is what we call a transverse wave. There's also another type of wave called longitudinal. I'll show you, I'll tell you what's the difference and show you some examples. Okay, so we will learn to compare and then we look at some examples of transverse and longitudinal waves. Okay, so just now when we see that, okay, a particle move up and down, so for this example here, the wave is traveling to the right hand side, right? The wave is traveling to the right hand side, but you can see that this particle is moving up and down. Okay, so the motion of this particle, right? Maybe I should switch to the slides for you to see, right? In this case, right, the wave is moving to the right hand side, but the particle is moving up and down, right? So it's quite clear that the motion of the particle is actually perpendicular to the direction of the wave travel. Okay, again, right, this motion of the particle is going up and down is actually perpendicular, right? If I draw a right angle here to the direction of wave travel, that is characteristics of a transverse wave. Okay, for a transverse wave, particles oscillate in the direction perpendicular to the direction of wave travel. Okay, now there are some other waves called longitudinal wave, whereby the particles actually oscillate, right? Remember, oscillate means travel to and fro to extreme points, right? Their oscillation is actually parallel to the wave travel. Okay, let's take a look at an example here. Okay, so if you look at this animation here, okay, for a transverse wave, if I were to stare at one particular particle, let's say this one, right, you can see that that particle actually moves up and down. But if you look at a longitudinal wave, let's stare at the particle highlighted over here. Okay, you can see that it's actually moving left and right, which is actually parallel to the direction of wave travel. In this case, is to the right hand side, you see. So all the particles, you can find any particle on the longitudinal wave, you will see that they oscillate, right, in the direction of the wave, which is horizontal, right, when the wave is traveling horizontally. Okay, so this is characteristics of a longitudinal wave. The particles actually oscillate in a direction parallel, this time, to the direction of wave travel, right? So this is the key difference between the transverse wave and longitudinal wave, which is the direction in which the particles oscillate Alright, so is it perpendicular to the wave direction, or is it parallel to the wave direction? Okay, that's the main difference. Okay, now at the same time, okay, we will see that later that the wave is made of crests and troughs. We'll tell you what is it about. While because now that the particles for a longitudinal wave, you know, is traveling parallel, we don't call it crest and trough, we call it a compression and rarefaction. Right? We see this in another part. Okay, so but first of all, what is the similarity? Okay, both require a source of vibration or disturbance. This is mentioned already. Okay, both involve some form of oscillation of the particles, just that the direction of the oscillations are different, right, for the two types of waves. Okay, what are some examples? For transverse wave is the typical ocean wave or water wave that you can see. Okay, just now you can see, right, the rubber duckling or the floating object actually moves up and down, right, perpendicular to the direction of wave travel. So that's water waves. Rope waves, definitely, right, you can see, right, you can try, right, find a rope or find a string. You can see that any point along the string will move up and down, which is perpendicular to the wave travel. Light waves as well. Alright, this is the type of wave that we can see. Okay, we'll learn more about that in the next topic. But another example is infrared. Alright, infrared waves. So this infrared wave is responsible for the thermal transfer mode of radiation. All these guys are examples of transverse wave, quite common. But the longitudinal wave is, for example, sound wave. Okay, so let's think about it. Sound wave. What creates sound wave? For example, the membrane in the speaker vibrates. Your vocal cords vibrate, right? So longitudinal waves such as sound waves also require some form of vibration or disturbance. When you speak, you put a finger on your throat. You can feel your vocal cords vibrating. Now that is the vibration that creates your sound wave, which is actually a longitudinal wave. Okay, maybe we will see a diagram later. There's another type of wave which is due to earthquake. We don't really experience this in Singapore, but seismic waves. Yeah, this is also longitudinal. We can't really see it because it's underground, right? Alright, to illustrate a little more about longitudinal waves, okay, of a sound wave, okay, so if you look at any speaker at home, okay, you can see that actually there is a very thin membrane, right, that will vibrate according to the music. Okay, so this is the vibration of this membrane will actually push the air molecules around the speaker, right, causing a longitudinal wave. Okay, so if we look closely into the particles, this is what actually happens, right? If I have the membrane that's vibrating to create sounds and music, what it does is it pushes the air molecules around it. Each little ball here is each little dot here is a air molecule. So what you see is that, you know, sound waves are being produced, longitudinal waves, right? Remember, for longitudinal waves, the particles, right, along the wave are actually oscillating or vibrating in the direction parallel to the wave travel, right? So if we stare, just pick any particle, right? Just pick any particle and stare at it. Let's say we pick this one. Okay, I'm trying to follow with the mouse cursor, right? You can see that it is oscillating to and fro parallel to where the wave is traveling. In this case, this is a circular wave, right? But if it's a plane wave, a linear wave, you will see the same effect. Remember to commit this table here to memory. Alright, you need to memorize practically every single part of this, including the examples. Okay, we can ask you for that. Okay, so next, let's look at the different parts of a wave. Alright, we call it the anatomy of a wave. Just like human body, there's different parts, different muscles, different parts of the bones. Okay, the waves also have different parts and they're all named. Okay, so we will look at what it means by the speed, the frequency, the wavelength, the period and amplitude of a wave. Okay, so this part here, section 4, consists of many names. This is when you need to commit things to memory. Alright, this is very easy. Actually, they're quite easy to remember. Right, so a few names here. Next, what it means by wavefront, yet another name. And this is the formula one of the formulas, main formula for wave that we need to remember. V equals to F lambda. I'll tell you what they are. Okay, so first of all, parts of a wave. Okay, so just now we were saying that a transverse wave is made up of crest and trough. Okay, so here we're talking about transverse wave, of course. Maybe you want to take note here. This is a transverse. Okay, remember that a transverse wave, right, the particles actually vibrate perpendicular to the direction of wave travel. Okay, in this case, the hand is the one that's creating the disturbance, right? The hand is the one that is creating a disturbance in the string. Okay, without the hand, the string will be just lying there straight. Okay, so by creating a wave, what we have here, okay, you have the particles, you know, vibrating perpendicularly, and the wave is traveling to the right hand side in this case. Now the highest point, okay, the highest point on the wave that the wave can actually achieve is what we call the crest. Okay, think of it as a crown, right? Crown, a crest. Okay, a crown of a king on the head. Okay, a crest. At the most bottom point that the wave can reach is called a trough. Okay, think of it like a drain, alright, a trough of a drain. Okay, now where is the there's the high point, there's the low point, and there is a center. Okay, this center is what we call the equilibrium point, which is this one, the center of a wave between the crest and the trough. Alright, so this dotted line here represents the equilibrium position. Okay, the equilibrium position, which is the center of the wave. So we call it the center of the wave. Okay, so what do we have here? We have the highest point called the crest, we have the lowest point called the trough, and the center of the wave is called the equilibrium position. Now, with this, we need to learn another term called the amplitude of the wave. Okay, what is it? The amplitude is a length. Okay, is a length. It's the height of the from the equilibrium, which is here, right, the equilibrium line, to the crest. This length is called the amplitude. Okay, the amplitude can also be from the equilibrium to the trough. Alright, so we can identify a few more amplitudes here. All these guys are amplitudes, mainly from the center point to the highest point, or from the center point to the lowest point of the wave. That is called the amplitude. Okay, so different waves can have different amplitudes. Okay, you will learn in the topic of sound. The amplitude has got to do with the loudness of the sound. The greater the amplitude of the sound, the louder the sound is. Now at this point in time, I thought it'd be useful if we come to take a look at this simulation here. Okay, so what you have here is a wave, okay, generated on an object. Okay, all these beats actually represent molecules along the object. Let's say this is a string, right? So each of these beats represent the molecule of a string. Okay, so you have this piston here that is creating the disturbance, right? Remember, all waves are created by disturbance, okay, along the object. In this case, it's the string, right? So you can see that, okay, the crest and the trough are actually moving as the wave is moving to the right hand side. Okay, so let's take a look. In this setting, I set the amplitude to be 1 cm. Let's check whether this is indeed 1 cm, right? So where is the equilibrium position? In this case, it's the yellow line. Okay, the yellow line is so-called at the center of the wave, you see, and the highest point, which is the crest, is represented along this red colored dot. So you can see that the particles don't go beyond the red colored dotted line. Okay, so where is the amplitude? Well, it is from the equilibrium position to the crest, the maximum position, right? So I can use this ruler to measure what is the length. In this case, indeed, it's approximately 1 cm. You can see that, right? Okay, so there's another way to measure the amplitude, which is from the equilibrium to where? To the lowest point, right? Okay, so I'm moving the indicator, the red color indicator, to the trough position, the position of the trough, which is the lowest point of the wave, and you can measure is also approximately 1 cm. Yeah, it's not super accurate though, but yeah, that's the setting, 1 cm, 1 cm. So next, okay, wavefront. Okay, wavefront. If you look at a wave, okay, if you see a water wave, you don't really see the wave as a whole. It's like this, right? This is only when you see it from the side view. But if you look from the top down view, what you will see is actually you will see lines, something along this line. Okay, you will see lines like this, right? This is how you will see a wave, right? Or for circular waves, you know, you will see if this is the center of the wave, right? You will see that you know, there's a lot of circles, right? If you drop a stone to the center, right? So this lines that you actually see, you know, on the wave is actually called a wavefront. Okay, but a wavefront, strictly speaking, is imaginary. It's just a mathematical line that joins all the adjacent points that are in phase. Okay, so there are a lot of terms here. Okay, but this one, first of all, please commit to memory. What do I mean by in phase? You will see that later. Okay, but for now, this is the definition. It's an imaginary line. You know, we can see it, but the wavefront can be theoretically anywhere along the wave that joins all the points that are in phase with each other. Okay, so a wavefront can be straight line depending on the wave, right? This kind of wave is a linear plane wave, right? It's so the wavefront is straight, but for this kind of circular wave, the wavefront is circular. Okay, so that's another term for you, the wavefront, to remember. Okay, I'll explain later what it means by in phase. Okay, all right. Next, wavelength. Okay, so we know that wave is traveling, right? A wave is traveling from one point to another. Okay, we need to define some form of length for the wave. Okay, and that is the wavelength. Okay, so if we see the wave as an object, then we can kind of define how long this wave is now. Okay, so we call it the wavelength. Okay, the wavelength, we use this symbol. This symbol is a Greek symbol. Okay, memorize first. Okay, so this Greek symbol is named lambda, Lambda. Okay, this is the Greek letter for L, right? Something like the Greek letter L, right? It's called lambda, right? So the wavelength or lambda of a wave is the shortest distance between two consecutive points in phase with each other. Okay, again, you see the word phase, right? I'll explain later what it means by phase. Okay, but to make life simple for you, by looking at the wave, how can we determine what is the wavelength? Okay, again, it's the length, remember. Okay, so there's three ways you can do it. One, by measuring the length between two crests. So let's say, looking at this crest and this crest here, the distance between these two crests is a wavelength. Alright, get the idea? Okay, we can also spot another wavelength from S to V. This is also the wavelength, lambda. They should be the same. Okay, that's number one, the distance between two crests. Number two, the distance between two troughs. Okay, so R and U, these two guys are troughs, right? Lowest point on the wave. The distance between the two of them is also the wavelength. They should be the same length. Okay, so number two, distance between two troughs. Number three, one equilibrium position to another one which is two positions away. Okay, so very wordy. Okay, the way that I would remember this is, if I look at a wave, okay, I start from one equilibrium position, in this case Q, right? And I will draw like a one full wave. Okay, what do I mean by one full wave? Look, so Q all the way up to this T. Okay, so I will draw like this. Okay, this is like one wave. Okay, so I'll draw this, and when I reach the equilibrium point again, okay, I will see position T, right? Now the distance between Q and T is also one wavelength, also lambda. Okay, so all these three lengths, you know, between two crests, between two troughs, and between two equilibrium positions that are two positions away from each other, these are all the same length, they are wavelengths. Okay, now number three is a little confusing. Let me try to draw another possible wavelength. Okay, full wave. So I can start from T, which is at the equilibrium position. Okay, I draw one full wave and I arrive at W. Okay, again, one full wave and I arrive at W. So this TW, this length is also the wavelength. Okay, so you can practice on your own to find another possible way to draw a wavelength. Maybe we can start from here. This is also another equilibrium position. So how does one full wave look like? It looks like this. Okay, so this to this is also one wavelength, lambda. Okay, moving forward, so we have three different ways to measure, right, the wavelength of a wave. Okay, so we're looking at the distances. Okay, so simply one wavelength can be a distance for these four different ways, right? So from here to here, from here to here, from here to here, and from here to here, right? So this guy here is crest to crest, this is trough to trough. Okay, while these two are equilibrium to equilibrium, two positions away. Alright, let's come back to this simulation again. Again, we have the same wave, same amplitude, okay? Now, our task now is to look at this wave and try to measure what is the wavelength of this wave, right? In order to do so, let me hit a pause here. Alright, I'm freezing the time and taking a snapshot of the wave, alright, along some time, okay? So, you can see that the amplitude doesn't change, it's still 1 cm, alright? So our task now is to measure the wavelength of this particular wave. So how can we do it? Remember, there are three different ways, right? From the crest to crest. So I'm measuring from this green bit here to somewhere here. Okay, so let me measure it. It's approximately 4.1, around there, 4.1 cm, right? This is 4.2, 4.4, 4.6, so on and so forth. Okay, so this is 4.1, right? So the wavelength of this wave is 4.1 cm if we measure from crest to crest. What's the second way? From trough to trough, right? So let's identify. This is one trough and this is another, right? So I'm going to place the ruler from here, approximately from here to this beat here. Also, approximately 4.1 cm. What is the third way? The more difficult way, okay, from equilibrium to equilibrium, two positions away. So let's start from here. This is one particular equilibrium position, one position away, two position away, or you can do as I did just now, okay, draw one full wave, right? So I'm gonna start from here and then I'm gonna measure one position, two position away, just at this yellow dotted line. Okay, you can see that, no, sorry, I move a little bit, right? It's about from dotted line to dotted line, that is approximately 4.1 cm as well. So this is how you can measure the wavelength of a wave. Let's come to the crazy concept of phase. Okay, it's a little abstract. Okay, if you don't understand, it's alright, but try to understand. Okay, so what do I mean by in phase, right? Okay, so 2 points on the wave, any 2 points on the wave, they are in phase with each other if they are at the same displacement from the equilibrium. So there's three conditions to fulfill. One is they are at the same distance away from the equilibrium. What do I mean by that? For instance, let's look at this guy here. Okay, this guy is at the distance, let's say d, from the equilibrium. Can you spot another point that is in the same distance from the equilibrium? Well, you can look at this guy also, right? This guy over here, also at a distance d. We can also look at this guy here, also at a distance d from the center. Or you can also look at this guy, also same distance, right, from the center, right? But not all of them are in phase. Okay, but why is that so? Because this is the first condition only. Okay, so first condition, they are at the same displacement or distance away from the equilibrium. Number two, they must be moving in the same direction at any point in time. Okay, so this is when we can filter away some of the points that are not in phase. Okay, so let's say, let me erase some of the markings here. Okay, let's say I'm looking at this point here. Okay, so this point is at a distance d from the center. I can also spot another point, let's say here, right, also at a distance d from the center. But are they traveling in the same direction at this point in time, or rather in any point in time? All right, so let's recall a little bit. This is important here. How do we tell whether how do we tell where are these 2 points going to move at this instant, right? If you recall back to the concept taught just now, what we do is we draw the wave at the next moment. Okay, this is a very poor drawing, but just bear with me. Okay, so at the next moment, the wave should have moved a little bit to the right hand side, right? So it should be at the blue line there. Okay, so let's look at where this particle, let's call it particle 1, let's call it particle 2, right? Where is particle 1 at the next moment? Well, it's over here. So particle 1 should have moved upwards. Particle 2 here, particle 2 also have moved upwards. So these two particles, they fulfill conditions 1 and 2. Condition 1, they are at the same distance from the equilibrium. Condition 2, they are both moving in the same direction at this point in time. Okay, so both are moving upwards. So conditions 1 and 2 fulfill. Number 3, they are moving at the same speed. Now this is something that we cannot tell from looking at the image, right? We can't tell, okay? But the shortcut is like this, okay? There are the two particles are in phase, okay? If, let me erase everything, okay? If they are one wavelength away from each other. Very simple, okay? If they are at one wavelength away from each other. So let's look at this particular point here, point 1, okay? Where is next? Where is one full wave? Well, one full wave, if I draw one full wave, you can see that it's here, okay? So any particle that is one wavelength away from particle 1, okay, will be in phase with particle 1. Okay, let me show you a simpler example. Okay, let's look at R. Okay, R at this point is at the amplitude, right? Amplitude. Okay, and R is going to move upwards at this moment because, well, R is at the lowest point already, so R is going to move upwards. Okay, so which another point, can you find another point that's in phase with R? Well, as I said, the trick here is look at one full wave away from R, point U. Okay, you can see that U is also at the amplitude, right? Furthest away from the equilibrium. Okay, and it's also going to move outwards at the next moment. Okay, and they're gonna move at the same speed. Right, this one you can't really tell, right? But again, the trick is find a particle that is one wavelength away from the point that we're interested in. They will be in phase for sure. Okay, so you can read this part, right? You don't have to fully understand what in phase means, but it definitely helps if you understand because it appears in two definitions here, the wavelength and the wavefront. Okay, so let's come back to this, right? Okay, wavefront is the imaginary line that joins all points that are in phase. That means if I can find a few particles that are in phase with each other, okay, I can find a line that joins these few lines. This line will be called the wavefront. Okay, so let's go back to this one for example, right? So just now we identified that R and U are in phase. Okay, let me continue the wave a little bit. Okay, so maybe I can find another point, U, V, W, X, right? So this is point X. Okay, so point R, point U, and point X, they are in phase with each other. So if I were to draw an imaginary line that joins through all this guy here will be a wavefront. Okay, get the idea? I can also draw another line through P, S, and V. This line will also be a wavefront. Okay, so if you don't quite understand this, it's alright. Just make sure that you commit the definition to memory. Okay, moving forward, wavelength again, right? Wavelength is the shortest distance between 2 points that are in phase. This is why I say, using that definition, I don't have to care about what 1, 2, and conditions 1, 2, and 3 mean. I just have to find 2 points, you know, that are one wavelength away from each other. So for instance, point Q, one wavelength away, point T. Immediately, Q and T will be in phase, right? Likewise, they both will be in phase with point W. Okay, they are all in phase because they are one wavelength away from each other. Okay, so this is a little confusing. Okay, but don't worry about that. Okay, you don't really have to fully understand what it means by in phase. Okay, okay. Next thing we have to learn is period. Okay, so Period means that of a wave is the time taken to produce one complete wave. By the way, you should have heard of this word period before. Where? A pendulum. Right? In case you forgot, right? Let's go back to the slides a little bit. Let's go back to the slides a little bit. Okay, now if you look at this pendulum here, right? Recall a little. The period of a pendulum is the time taken for it to finish one complete oscillation. Okay, which is, for example, A to B to A. That's the time, that's the period, right? So if I were to time it now, 1, 2, 1. Okay, that time to complete A to B to A is the period of the pendulum. And we see that just now, right, that the particle along a wave also follows the same motion. Up, down, up, right? So we now come back to the same simulation again, the same wave, right? And now our task is to figure out what is the period of this moving wave, right? So you can see that I can set on the timer here, okay? So I'm gonna do it this way, right? I'm going to stare at this green bead here, the very first molecule, right, along the wave, okay? I'm gonna time the time it takes to move from, you know, from the top point, which is the crest, to the next crest. Because you remember, a full wave can be drawn, right, from crest to crest, you see, all right, or trough to trough. We will do that later on, okay? So I'm gonna start the stopwatch when it reaches the crest. I'm gonna pause when it reaches the crest again. So ready, here we go. Trough to crest. All right. So this wave is the period of this wave is approximately 0.66 seconds. All right, I'm gonna do so from trough to trough as well. Okay, so let me put the marker down here. Okay, I'm gonna reset the timer. Once it reaches trough, I'm gonna start, and then I'm gonna stop again when it reaches the trough again. Ready? Here we go. Trough, crest, trough. Okay, 0.64, right? Okay, but it's really close, because remember that there's this thing called human reaction time, right? So when I press the stopwatch, the start and stop, right, there's some error here and there. So approximately there, right, the period of this wave is about, you know, 0.64, 0.66, 0.65, around there. Okay, right, so a period is the time taken to produce one full wave, one complete wave. Okay, so it can be found by timing. So remember, a period is a time. So we're no longer talking about distance here, right? When we talk about distance, that is wavelength. But now we're talking about time. Time is, period is a time. It's a time quantity, right? So it can be found by taking the time between two crests. That means if I see one crest, I will start timing. Until I see the next crest again, I will stop the timing. That time is the period, right? So two crests, two troughs. Can you see it's the same way as we measure the distance for wavelength, right? For wavelength is the distance between two crests or two troughs. For period is the time between two crests or two troughs, right? Number 3 is the same, okay? Between equilibrium points that are two positions away is the same as point number 3 for wavelength rather, but wavelength is the distance. Here we're measuring time, okay? So that's period for you. Okay, frequency. Okay, so frequency is related to the period. Okay, first of all, frequency is the number of complete waves done every second. Okay, all right. So there's the formula here now. Okay, frequency is 1 over period. So that's the formula over here. Okay. Okay, so let's recap a little. What's the difference between these two? Period is the time taken to finish one wave, to complete one wave, while frequency is the number of full waves every 1 second, per second, every 1 second. So if you look at the definition alone, you can tell that their relationship is inverse relationship. Okay, F equals to 1 over T, or T equals to 1 over F. Inverted lah, okay? Alright, and frequency has a very special unit, hertz. Capital H, small z. Alright, but period, because it's a time unit, SI unit is a second, right? The SI unit for time. So you have period, you have frequency, right? Okay, so why are we learning all this? Okay, let's relate a little bit. We have wavelength. Okay, remember, if we see wave as a moving object, we can talk about the speed of the wave, just like the speed of an object. But what's the formula for speed of an object? Speed equals to distance over time, right? So if I want to see a wave as an object, then if I want to find the speed of the wave, then I have to measure some distance that the wave has traveled. In this case, we use wavelength as the distance. And I also need to measure some form of time. The time here that we're talking about now is the period. Okay, so again, if I want to measure some form of distance, take reference, I will use the wavelength as a reference for the distance that the wave has traveled. I will use the period as a reference for the time taken to finish one wavelength, right? So using this concept, we can come to the final formula, which is the speed of the wave. Okay, the speed of the wave is the distance traveled by the wave every second, which is actually the same formula, the same definition as the speed for any object. Okay, now, so when I replace, for example, just now I was saying, right, this speed equals to distance over time. Now I'm going to replace distance with lambda. I'm going to replace time with period. I'm going to get v equals to lambda over t, right? But lambda over t is the same as lambda times 1 over t. And 1 over t is simply the frequency. Remember that, right? Frequency equals to 1 over t, the period. Alright, so I'll replace 1 over period with frequency, and I have the final formula here, v equals to f lambda. Okay, the speed of the object is given by the frequency of the object multiplied by the wavelength. Okay, so let's write it down. Speed of the wave is obtained by multiplying the frequency of the wave by the wavelength of the wave. Okay, so I hope this is clear, and because this is a speed quantity, it also has SI unit of meter per second. Okay, now at this point in time, let's come back to the same wave that I've been dealing with just now, alright, all the while. Okay, so let's look at the frequency here, right? I have set the frequency to 1.56, right? And let's recall a little bit, what does it mean? 1.56 Hertz, the frequency, means that every 1 second, approximately 1.5, wave should have been produced. So again, 1.56 Hertz for a wave means that every 1 second, 1.56 wave has been produced, approximately 1.5. Okay, and just now, okay, we also discussed that frequency f equals to 1 over the period, and I just timed the period of this wave to be approximately 0.64 seconds, you see. So let's do a calculation to check whether the formula is true. Okay, so I bring out my calculator here. Okay, I will take 1 divided by 0.64, that is the period, right? So 1 divided by 0.64, I should get approximately 1.56 Hertz, quite close, right? So that means, of course, this timing, because I time it by hand, is subjected to human reaction time. Okay, so also I would like to show you what happens when the frequency increases. Okay, so right now you see, let's pause here and let's measure the wavelength. Okay, the wavelength is approximately 4.2, around there, 4.2 cm. Okay, now let's see what happens if I double the frequency to about 3, right? 1.5 double is 3. Okay, so let's see what happens. Okay, first of all, you see that there are now more waves produced within the same length, within the same space here, you see. Okay, and 3 Hertz essentially means that 3 waves should have been produced every 1 second. Alright, and I'm going to try to pause at the correct timing here. Okay, now let's measure the wavelength now. It should be from crest to crest, approximately 2.1, which is kind of half of what we had just now, right? Just now we had 4.2, now you have from crest to crest is 2.1, which is half, you see. So what happens here? When I double the frequency, the wavelength actually halves. Why is that so? let's go back to the notes here. Let's go back to the formula. Given the same speed of the wave, if I double the frequency, the wavelength should be halved. Alright, so frequency and lambda, they're kind of inversely related to each other. When I increase the frequency, the wavelength should go down. When I decrease the frequency, the wavelength should increase. I should see a longer wave, you see, if the frequency is reduced given the same speed. Okay, so let's try again. Let's now reduce the frequency to real slow, to real low, right? Low frequency. And you can see that the wavelength is very, very long. Here on the screen, you can't even see one full wavelength. Okay, I increase the frequency a little bit. First of all, this thing should move up and down faster. Okay, you can see that. Let me pause. So now the wavelength is from here to here, much longer, you see, when the frequency is much lower. Alright, so I hope that helps you to understand what this formula is about. Alright, so now we have seen through the simulation what it means by frequency and amplitude and wavelength, of course. Okay, let's try one example. Okay, let's consolidate what we have learned in this particular example. Okay, this is a very typical question. Okay, so let's take a look. This information of a wave is represented by two graphs shown below. Okay, so when we look at a graph, what is the first thing that I always say? We must always look at the axis titles, because that is what gives meaning to the to the graph. Yeah. Okay, so in the first graph we have displacement against distance. Now, if the x-axis is a distance, then one full wave like this, right? This part here gives us wavelength, because wavelength is a distance. Remember that. Okay, but on the other hand, for this right hand side one, right, the one on the right hand side, the axis is time axis. So one full wave here tells us what? Actually tells us the period, capital T, right? Sorry about that, let me write again. Okay, so this one full wave now tells us the period, because period is a time unit. Alright, so different graphs will tell us different information about the wave. Alright, so this graph here gives us wavelength because it's a distance x-axis. Okay, so first of all, what is the wavelength of this wave? Alright, we can obtain by three ways, right? One is distance between two crests, right? In this case, 0.5 to 1.5, we obtain that this wavelength is 1.0 meters. Or the other way is between two trough. From 1.0 to 2.0, you also realize that the wavelength is 1.0 meters. Okay. Of course, you can try the third way on your own. For example, from here to here. Okay. You should get the same result. Either ways, what we obtain from this graph, the information is lambda, which is the wavelength, equals to 1.0 meters. Okay, moving on next. Okay, this graph should give us the period. So from trough to trough, right, the period is 4.0 what seconds. That's the unit, right? Because the unit is in seconds. Right, we can also try crest to crest, right? From 2.0 to 6.0, we also get the same result. Right, the period is 4.0 seconds. Remember to work everything in terms of SI units, right? In this case, seconds and meters, right? If you're curious about the y-axis is displacement. Okay, displacement simply tells us that where is the particle from the equilibrium, right? So just now we were saying that, let's say I have the equilibrium line here and I have the wave, right? Let's say this point here, it is at a distance, some distance d from the equilibrium point. Now that is the displacement. Alright, and the displacement of the highest point to the equilibrium is simply the amplitude. Remember that, right? Okay, so you can see for both graphs, even though the x-axis are different, they actually carry the same information on the y-axis, which is the amplitude is 0.05 meters, because they are describing the same wave. Okay, so we have obtained information about the wavelength and the period from two different graphs. Remember, check the axis always. Alright, moving on. Question asks, what is the wavelength of this wave, right? So we already have the information, lambda equals to 1.0 meters, simply by looking at the first graph alone. What is the period of this wave? We also have obtained it, 4.0 seconds. T equals to 4.0 seconds by looking at the second graph alone. Now, what is the speed of this wave? So for this is the point you have to recall what is the formula, right? We have V equals to F lambda, okay, where this F frequency is simply 1 over the period, right? Because we have no information about frequency, but we have information about the period. Okay, so we can simply replace F as 1 over T times lambda. Okay, so you can just put in the information. T is 4.0 and lambda is 1.0 meters, right? This is a multiply, right? Multiply between the two of them. F times lambda, 1 over T times lambda, and you got your answer as 0.25. What is the unit? SI unit, meter per second. Okay, because lambda is given in meters and period T is given in seconds. So there you go. Actually, it's quite simple. You only have two formulas to work with, this and this. Right, the difficult part is extracting the information, right? And quick tip for you, okay, yeah, as I was saying, please do check the x-axis because different x-axis give you different information. If the x-axis is a distance axis, then you should be able to get the wavelength about the wave. If it is a time axis, then you should be able to get the period of the wave. So that's it for this topic. Okay, let's do a quick recap. Okay, on the whole topic, it's really huge though. Okay, so at the start, we learned about wave. What's the meaning of a wave? It's a disturbance that transfers energy but does not transfer or transport matter. Okay, we also learned about this looking at each particle along the wave, how it actually moves. For a transverse wave, okay, the particle moves up and down, okay, in an oscillatory motion, up and down. But for a longitudinal wave, the particle actually moves left and right. Actually, rather I should say parallel to the direction of wave travel. So here we have the difference between transverse and longitudinal wave. We have seen some examples. Okay, we also learned about the names, the meaning of the different parts of the wave. Okay, you have the crest, the trough, which is the highest and lowest point. You have the equilibrium position, which is the center position of the wave. Okay, the amplitude being the distance from the equilibrium to the crest or the trough. They should be the same. Okay, we learn about what is a wave front. Basically, this is not super important. Don't be worried about that. Okay, more importantly, wavelength, right? Is the distance, or rather, we should say the shortest distance between two consecutive points that are in phase. For example, between two crests, that's one wavelength, or between two troughs, that's one wavelength, or between 2 points that at the equilibrium but 2 positions away, right? So remember I was saying draw one full wave, right? And you'll be able to tell what is the wavelength of the wave. Okay, so with the wavelength, we also have the period, right? We have the distance, we have the time. Right, the time is the period, time taken to finish one complete wave. We also have the frequency, which is the number of waves produced every 1 second. So they are inverse relationship with each other. F equals to 1 over T. This is their first formula. Okay. Now, then we come to the final formula, which is related to the speed of the wave. How fast is the wave traveling? Speed equals to distance over time. In this case, instead of D, distance, we use wavelength. Instead of time, we use period. Okay, so V equals to lambda over T, or V equals to F lambda. I will choose to remember this formula, V equals to F lambda. Okay, and then we have seen one example rather of how the different axes of different graphs actually tell you different information about the wave. From that, you can actually do some calculations applying the formula. So that's it for this chapter. I don't know whether it's big or small. To me, it's rather big, right? Because there's a lot of names and formulas to remember. Okay, I hope you can commit all of them to memory. Okay, I'll see you back in class Take care.